Hey everyone, hope your day is going well, and I hope you're ready to feel kind of dumb. Or at least I'm gonna feel dumb. I've watched a few videos on this and listened to people talking about this, the incomprehensible scales that rule the universe. We just can't wrap our heads around. But I see Brian Cox. I want to listen because the man has such a great way of, you know, telling stories and explaining things about the universe and such with such passion that he talks about it. Even if I don't understand it, I still watch it, man. So let's go. Thank you for joining me. Let's listen to Brian.
When we think about the size of things, we tend to think of the size of things with reference to ourselves.
What do you mean?
So, the foot or the meter or those things, or the inch or the centimeter, what are those things? Ultimately, historically, they're based on properties of the human body. So they're based on biology. And that's what we did historically, because why would you do anything else? Is that fundamental? Well, the answer is no. It doesn't tell you anything profound or deep about the deep structure of the universe. But of course, the history of physics tells us, as we go into the 17th century, the 18th century, the 19th century, 20th century, we then begin to understand that there are things that are much bigger than us and much smaller than us.
Jeez,
we're looking, I suppose, for units of measurement that you could imagine if we met some aliens from some different civilization. They might not even have arms, right, or feet, but they might be very different in size and scale from us. So what would the common language be? Is there some unit of measurement that we could all agree on? I'm Brian Cox. My full title is Professor.
Yeah, I think about those, just in terms of storytelling and having fun with my imagination. He's actually thinking about it from a scientific perspective, preparing for when the alien comes. That's good. You got to be prepared. Yeah?
Professor of Particle Physics at the University of Manchester, Royal Society Professor for Public Engagement in Science and Visiting Scholar at the Crick Institute. Or you could just call me Brian. What are the fundamental quantities, as far as we can tell, that really tell us something about the structure of nature? So one would be the speed of light. Everything that is massless travels at the speed of light, at this speed, whatever it is. If you have any mass at all, you cannot travel, you cannot accelerate to this speed. Another one would be the strength of the gravitational force. So what is the force between two objects of a particular...
Wow, George Lucas would have something to say about that, huh? What is the force?
So what is the force between two objects of a particular mass? Or in Einstein's theory, how does a particular amount of matter or energy distort the fabric of the universe? The number that tells you about that is Newton's gravitational constant, which was first measured back in the 1780s, 1790s.
Damn, he lost me at foot. I don't even know what a foot is. I use the metric system. So even there, he lost me. Hey.
And then there's Planck's constant itself. In 1900, Max Planck made a revolutionary proposal. You could say, for example, that there's a fundamental limit on how accurately we can know the position of a particle and the momentum of a particle. You can't know them both with absolute precision. There's a fundamental limit, and it's around about Planck's constant. Planck first introduced it in the context of the frequency or the wavelength of light emitted from hot objects. Photons. What's the energy of a photon? A packet of light. It's Planck's constant multiplied by the frequency. So those three things, the speed of light, strength of gravity, and Planck's constant, allow you to define some distances, a particular distance called the Planck length. And it's a tiny length. It's about 10 to the minus 35 meters.
That's not a lot.
35 naughts, 1 of a meter. So we have this fundamental, it appears, length scale in the universe, unimaginably small. How could you picture that? If you take a proton and expand it to the size of our solar system. So imagine that, the nucleus of a hydrogen atom, and you imagine expanding that to the size of our solar system out to the orbit of Neptune, then something that's the Planck length would expand to, let's say, a virus or a living cell. So the ratio in size between the Planck length and the cell, which we can just about see under a microscope, is the same ratio as a proton to the solar system. It's unimaginable.
We always think about the big things. Pause. But we never consider the small. It's unimaginably small. Insert Steve Carell meme.
Imaginably small.
Oh, he actually.
So how do you observe something that's very small? You have to shine light with a very small wavelength onto this thing to see the tiny thing. The wavelength can't be bigger than the tiny thing, otherwise you won't see it. But remember, quantum mechanics tells us that the smaller the wavelength of the light, the higher the energy of the photons. So I have to start bombarding this thing with higher energy photons to see it. What happens if you try to approach something that's the Planck length? You get so much.
My brain is the size of a Planck length right now. I'm still trying to grasp that concept, and now he's moving on. He's moving on. Oh, okay. Gotta center myself here. Man, but he does see even that, all these equations and terms that most of us don't understand or haven't even heard of, he does manage to give us a great reference and to get an inkling of an understanding. That's why I love watching his stuff, man. He's so
what
good.
happens if you try to approach something that's the Planck length? You get so much energy in there. What you do is you form a black hole. And then you put more energy in, you try to see what's going on, and the black hole grows. And so you get to a point, which is around the Planck length in size, where you can't, in principle, try to resolve the structure of this thing. So I think it is legitimate to make the argument that given what we know about the universe, given the measurement we make of the strength of gravity, the measurement we make of Planck's constant, and the measurement we make of the speed of light, then there is something fundamental about this very tiny length, 10 to the minus 35 meters.
Wow.
Of course, the things we can really get a feel for are things that are around, let's say, a few inches, a few centimeters to a few meters. But then when you start to talk about the distance to the planets, or the distance to the sun, the so-called astronomical unit, 93 million miles. What does 93 million miles mean? So look at the moon. The moon is the same radius on the sky as the sun. You know that because of total solar eclipses. It is a coincidence based on the way that our solar system has evolved, but it's a nice coincidence. So we can perhaps conceive of what the sun looks like on the sky. 93 million miles away. You can fit 1 million Earths inside the sun.
That's crazy.
So how do we conceive of that?
That is wild. If you think about all these coincidences that he's talking about, if you don't believe in the simulation, because sometimes I do, man. Sometimes I do. A lot of NPCs in my neighborhood. But, we're just close enough to get a little bit of that heat that we need, but just not too close so we evaporate, and not too far so we all freeze. We got a little bit of a moon taking a hit, some of the meteorite hits for us, all of that. It's like, really? I mean, if you would tell a story like that to somebody, no, you're making this up. It's too convenient. It just works out. It's wild. But then we have the counterweight of humans screwing everything up. So that is that's when you know, okay, we got that as a variable.
You can fit 1 million Earths inside the sun.
So how do we
conceive of that? The radius is something like 100 times the radius of the Earth.
That's a big ball of fire.
That means that if you got in a passenger aircraft, well, it'd take something like a year to fly around the sun in a passenger aircraft. It becomes inconceivable. And the sun's quite a small star.
Well, you could fly on solar energy.
So then we start to think of bigger distances. So the most distant object that we created.
Oh,
we
yeah,
built
it's still going, huh?
with Voyager 1
That's
spacecraft.
crazy.
3, 2, 1. MDS, we have ignition. We have a liftoff.
Is now well over 150 astronomical units from the Earth, 150 times the distance from the Earth to the Sun. What does that mean? It takes light over 22 hours to reach it. So a signal at the speed of light to go to the most distant object we are in communication with, which has been flying since the 1970s. And then we have 365 times that, a light year, which is to the frozen edge of the sun's influence, the edge of the Oort cloud. 4 times further than that, you get to the nearest star, the Proxima Centauri, the Alpha Centauri system. That star about 4 light years away or so. So that's inconceivable. And then you start to talk about a galaxy then, the Milky Way galaxy. We're all in orbit around the center of the Milky Way galaxy. How big is this collection of stars? Somewhere between 200 and 400 billion suns in the Milky Way galaxy. About 100,000 light years across.
Jeez.
And then you say, well, what about the nearest galaxy? So you go outside on a clear night where there's no moon and it's dark, away from the city lights. I've never seen that. I need to see. And if you know where to look, you can just about see our nearest neighboring large galaxy. It's called the Andromeda Galaxy. That galaxy is 2.5 million light years away. It means the light entering your eye began its journey before we had evolved on Earth.
It's crazy that we're seeing light from, we're seeing history. If we look up, we're just looking at the past. It's crazy. Jesus. My imagination always runs wild with these kind of things, I love it. I love thinking about these things and what's out there. If they have TikTok and stuff, because that's important.
And then you start to say, well, what about the other galaxies? So we've measured galaxies now out to what we close to the edge of the observable universe with instruments like the James Webb Space Telescope, from which the light has journeyed for over 13 billion years to reach us. 13,000 million years to reach us. And the universe has been expanding in that time. So the most distant thing you can see in the universe that we can detect light from is called the cosmic microwave background radiation. So the cosmic microwave background radiation is light that was emitted 380,000 years after the Big Bang. So that's been traveling for 13.8 billion years or so across the universe to reach us. But then if you ask the question, where is that place now, the place that it emitted that photon from the cosmic microwave background radiation that came across the universe for 13.8 billion years into our detectors, where is it now? Because the universe has been expanding. You get an answer which is something like 46 billion light years away now. So you might say, well, the radius of the universe is 92 billion light years or so. It isn't, because we know that there's more universe beyond that. That's just as far as we can see.
Somebody has to turn on the lights over there.
And given the accuracy of our measurements at the moment, might be infinite in extent. And that genuinely is inconceivable. When we contemplate the size and the scale of the universe and our place within it, which you're forced to do when you think about the distance scales and the sheer size and age of the universe, then I think it's very natural for us to tend to come to the conclusion that we don't matter at all.
Wow.
But
no shit,
one of the great joys
takes the pressure off
about essentially being a scientist is that you can come across a point of view and you think, I hadn't thought of that. And I found it happened to me recently. I was reading a book by David Deutsch, who is one of the greats, one of the founders of quantum computing. And he made a point, which I had heard before actually, in a book called The Anthropic Cosmological Principle by John Barrow and Frank Tipler, which is a huge influence on me. But David Deutsch and Barrow and Tipler pointed out that it's not necessarily the case that life will always be a speck, that life remains insignificant on a cosmic scale. You shouldn't assume that. Because if life persists sufficiently long and becomes sufficiently knowledgeable and powerful, then it may be able to influence larger structures, not just planets and not just solar systems, perhaps not just even galaxies. You almost say that life manipulates the universe such that it becomes immortal. And it's a very beautiful idea.
Nice. Man, I love hearing him speak. He's so good. Yeah, man. It's incomprehensible. Like I said, for me, it takes the pressure off. If it's been existing for so long, it will exist for a lot longer, and I'm happy to know that everything will be okay. Before, after, whenever it starts all over again, and it implodes back into a little pin, and it explodes back into a new universe. However, that will work, I don't know, but I'm confident. Civilizations have been out there. Maybe they're still out there. There will be other ones. They've come and gone. They created music that we will never hear, and they might have made some very viral TikToks. I don't know, but I think so. Hey, thanks for being here, everybody. See you in the next one. Peace.